Hey everybody, welcome to video 4 in the basic electrical series. So the last video we talked about what a complete circuit needed. We talked about that term continuity that we all know and love now, and we learned how grounds work, right? So in this video, our agenda is to talk a little bit about circuit protection, what it is, how it does it, control devices, aka switches. Then we're going to get a little bit into where should voltage drop in a circuit. And then we're going to get through the whole time. We'll probably talk about symbols, but I'm going to talk about some miscellaneous symbols that you're going to want to know when you're looking at a wiring diagram. I'm just going to talk about the basics right now. I'll leave the higher end stuff for an electrical class. And then we're going to get into AC and DC. No, not that AC DC. AC voltage and DC voltage, or AC current and DC current, and we'll just talk about that briefly. So let's talk about circuit protection. Circuit protection is exactly what you might think it sounds like. It is protecting the circuit. Now, what do circuits have to be afraid of? What do we need to protect them against? They don't like excessive current flow. Now let's go back to the first video and we talked about what amperage was, or what current flow was and all that. Current flow, aka amperage, aka intensity, is referring to the movement of the electrons, right? We know that's what electricity is, but when we talk about current flow, that's what we are referring to. So when we get excessive current flow, we get too much electron movement for what the circuit has the capability for. And in a circuit, our restriction does become our wiring and things like that, the gauge, the thickness of wire, and as well as a couple of other things. So we need to maintain a particular amount of current flow. What's going to determine the amount of current flow in the circuit? Let's go back again to that teeter-totter. Remember the relationship between amps and ohms? So if we are going to try to figure out how much current flow I have in my circuit, let's look at the resistance. If my circuit has a lot of electrical resistance, it's going to have very little current flow. Again, it all pertains to voltage as well, but we're all working with a 12-volt battery right now because it's not a hybrid class. We're just talking about the conventional 12.6-volt battery that comes in most vehicles. Resistance is going to determine the amperage flow in that circuit. And so when the circuit was built, we know the resistance engineered in that circuit of the motor, of the light, whatever it might be, and we will fit the rest of the circuit with the gauge of wire that is needed. You will find starter circuits and things like that are going to have a whole lot of amperage flow, a lot because of the mechanical resistance involved, but high amperage flow circuits are going to require thicker gauge wire. While tiny little circuits, especially computer controlled circuits that are very low amperage, have really thin, tiny wires. So if I try to shove a whole lot of amperage through a thin, tiny wire, we are going to burn that wire up. And most of the time when we're dealing with amperage spikes, so we obviously engineer, not we, but the OEMs will engineer the proper thickness gauge wire for the circuit, and everything's all hunky-dory and wonderful. What about when something goes wrong? And that's where this comes in, the circuit protection comes into play. What can go wrong? So I'm going to talk in a later video about things called shorts, or low resistance faults, and these shorts or shorts to grounds, they can create amperage spikes. What happens is most commonly bare wire will touch the bare metal of the frame. And remember when we talked about grounds, we're using the frame for electrical, as part of our electrical circuits. So what we don't want is to bypass the load. Remember I said electricity always needs something to do. If we don't give it something to do, it's going to burn up and create something to do. It's got to get rid of that voltage. It's got to get rid of all that energy. And most of the time it's catching things on fire because of the high temperature, of the high amount of current flow. So what determines that current flow? Again, back is the resistance in that circuit. So however much ohms is in this light bulb, or that this light bulb provides, that will determine the amount of amperage in the circuit. What if I was to bypass that? What if I was, because we're using chassis ground here to come back to the battery for our continuity, the current flow, but we got to get rid of the voltage here, right? What happens if I bypass that? And let's say, and again, we'll talk more about this later, what if some wire rubbed through, bare wire, the insulation rubbed through so it's bare, and it touches somewhere bare metal on the chassis, engine, somewhere like that? Electricity is lazy and it will take the shortcut and go straight back home. But the problem is what have we done with the resistance in the circuit? It went from high to nothing, or very, very, very little. And so amperage is going to spike up like crazy. Well, without any circuit protection, it would create a fire. The amperage flow would spike up, the thickness gauge of wire wouldn't be able to handle it, and it would heat up so much so that the wire would actually, the insulation would catch on fire, and it would get hotter and hotter and hotter until it just melted, and now there's no continuity, so it would just break somewhere. And no ground, no continuity, no flow, it would break the circuit and it would cease to get hot. But we don't want to do that because other things in the car catch fire too, like interior and things like that. As much as we try to make it not flammable, if we're talking really high temperatures, it could put us in danger. So getting to the point, back to circuit protection, that's why it's there. What we do is we build in a weak link in the circuit, essentially, purposefully, that is meant to take the amount of current flow that is usually rated a little bit above what the operating current flow is. And if it surpasses the current, the amperage surpasses what our circuit protection is rated at. Let's say whatever you're using is rated at 5 amps. If we increase past that 5 amps, the current flow will be too much and the circuit protection will disconnect the circuit to save the circuit so you don't catch the circuit on fire. So what do we use to do that? I'm going to talk, there's many different ones, but I just want to talk about the 3 probably most common ones you will see out in industry. Fuse is first and foremost going to be the most common one that you're going to see. And we don't just draw fuses in there. I know you guys have seen my lovely pictures that I've been drawing here, but I'm going to try to continue to incorporate more and more electrical symbols rather than just drawing. And that's what the squiggly little line has been. That is actually the electrical symbol for a fuse. So I will include some pictures of what fuses look like inside of the PowerPoint presentation, so you can go ahead and look through Canvas what the fuse looks like, what a blown fuse looks like. But essentially inside, what we're looking at, and I'll explain the fuse, but I won't get too into everything else. I'll leave that for an electrical class, an Auto 54 class. But what we're looking at, and let me use a different color actually. So we're looking at, we have to make a connection in and out, right? Just like here, coming from the battery in and coming out to the rest of the circuit. We'll go ahead and close that part of the circuit there. So we've got a connection in and a connection out. Obviously, they need to be connected for continuity, that continuous path, right? If we don't have a path, no flow. So what we do is in between these connections, we will make a little skinny, weak link that connects one side to the next. Let's say this fuse is rated at, because they're usually pretty clear, and I know my picture's getting a little crowded here. Let's say on top the fuse says it's rated at 5 amps. When this reaches past 5 amps, it's usually not, they're not super sensitive to where like right at 5 amps it'll pop, but once it exceeds 5 amps, this weak link, we call it a sacrificial element because that's exactly what it is. When current flow gets past this will get so hot, our sacrificial element will get so hot, it'll actually melt and burn up the connection. So this side no longer connects. The inlet no longer connects to the outlet, just like that. Essentially opening up our circuit so we no longer have a path for current to flow. We break our continuity. If we have, again, remember, and I know for some of you guys, you're like, yeah, you keep saying that. Again, keep your eye on the ball. Continuity, I cannot emphasize it enough. It needs to be a part of your life. Understanding continuity. So if our fuse breaks because too high of current flow, too much amperage, we have no continuity, my circuit no longer works. But it's doing this to protect the circuit. So if you're dealing with a circuit not working because the fuse popped, the problem is not the fuse most of the time. Sometimes you get faulty fuses every once in a while. But most of the time the problem is not the fuse. The fuse popping is a symptom of a short circuit of some sort, an amperage spike. And so if you keep putting in fuses and you're like, man, these crappy AutoZone fuses, sorry AutoZone, they just keep popping. They must be, super bad. I'm going to go to O'Reilly. Guess what? You're probably going to pop those ones too, because the problem is not the fuse. The problem is the short circuit that is popping the fuse. And for those of you who are like, oh, I could just put, it was 5 amps, I'm just going to go ahead and put a 15 amp, a 20 amp. That circuit, the wiring thickness and everything, that was rated at 5 amps. And so if you put a fuse that is too strong, that is stronger than the rest of the circuit, everything else in the circuit becomes the fuse. And the fuse is no longer a fuse, if that makes sense. So really try to refrain from putting things like pennies or paper clips or just bigger fuses in place because the fuse keeps popping. You need to fix the problem. Now, most common are fuses that we use. The symbol looks like a little squiggle line in between two dots, or some vehicle manufacturers in their diagrams like to use, I don't like using this one because it looks too much like a switch in my opinion, but this one's pretty much a straight line with a box and sort of two dots connecting, but it might look like that. So if you see that, that's probably going to be a fuse as well. Again, it depends on the OEM on which one they decide to use. And I'm just using the common symbols. There are other manufacturers that use their own special symbols, but they should be close enough. Another one that we use is what we call a fusible link. It works the same way as a normal fuse where it's got the sacrificial element, except it doesn't have blades. There's other fuses that don't look like this, by the way. There's the glass fuses and stuff. Again, more for an electrical class or a tune-up in electrical class, not for an Auto 50. All you need to do is know what it does. But neither here nor there. Fusible links instead use, and there are different types of fusible links. Ones are very similar to fuses, where it has a little sacrificial element between two contacts in a plastic casing. Others, it's actually just a piece of wire, essentially, that is sort of connected or soldered in the circuit that is actually a thinner gauge and is meant to burn up before the rest of the wire does. And the symbol that looks like that is going to be similar to a fuse, but more like a wiggly worm. And that is your fusible link symbol. I've seen fusible links symbols in different OEMs. Again, this is a common one that is used. The last one I'll talk about is what we call a circuit breaker. Many of you are familiar with this because we use these for our houses, right? It does the same thing. However, fuses and fusible links are destroyed once they have surpassed their threshold. Circuit breakers do not. Circuit breakers instead actually use, and I will include pictures as well in the PowerPoint presentation on Canvas. Circuit breakers use a bimetallic strip or some sort of metallic strip that once it reaches a particular temperature will actually warp. So let's say it was flat. Let's use these tapers here. Let's say this metallic strip was flat, making a connection between a contact. When it gets too hot because of too much current flow, we get this warping, and it will actually, paper's not wanting, it will actually bend up and off two contacts. I wish I thought this through a little bit better. let me use something a little bit stronger. So let's say we're making a contact here from inlet to outlet in our circuit, and we get a temperature spike because of the amperage flow is too much, right? What will happen is this will warp up because of the heat, and it will disconnect the connection. Now, most of the time circuit breakers in cars are self-setting. So when it cools back down, it will come back and make the connection. The ones in your house are a little bit different. They do the same thing, but you have to reset them. So they're a manual reset. And in cars, we usually use the self-reset. Circuit breakers look a little bit different. Oh, I didn't finish drawing this one. Circuit breakers look almost like a banana, and you'll have to excuse my wonderful drawing here. They kind of look like a banana skateboard. Again, different OEMs, especially German manufacturers, use different symbols for different stuff. But this is the general symbols you guys may see in your book or online for all your circuit protection. So this is circuit protection. That is how it works. I'm going to go ahead and erase this here, and I just want to sort of recap quickly as I draw my fuse back in. So this is my circuit working normally, right? I close my switch. My light bulb lights up. If I had an issue where I had an amperage spike in my circuit, my fuse with the sacrificial element or my fusible link, whatever it may be, is going to melt and break. Now the problem is, again, continuity. So moving a little bit ahead of myself here. What we have here, if my fuse is intact, I have a path for electrons to flow through the fuse, through my switch, through the light bulb, and right here we've got a symbol for chassis ground. What that tells me is through the chassis, we're going all the way back to the negative of our battery, right? Our continuity, our continuous path for electron flow. When we lose continuity from popping the fuse, we no longer get any of this electron flow from the battery. So it all stops right here. Electrons will come out and be like, oh, it has no path to ground. So we get no electron flow. We'll even lose it here. You may get voltage or pressure, but no actual electron flow. So that would be a loss of continuity, which means our light bulb will not light up. So that's what the fuse or fusible link is going to do. Same with circuit protection. Again, circuit breakers may be used in something like power windows or your turn signals, things like that, right? Where it works for a little bit, it heats up, warps, turns off, turns on for a little bit, turns off. That's how flashers sort of work in a similar fashion. So that is our circuit protection. The next on our list is control devices. A control device is a fancy term for a switch. So right here, I've got these tiny symbols. So I will draw a larger symbol. Your switches will generally look something like this. So we've got a connection in and a connection out. Single pole, single throw switch, toggle switch. And what this tells me is when I want to close the circuit to provide continuity, right, if my switch, sorry, we'll redraw our fuse there. That's a horrible fuse. Try that one more time. It's not much better, but it works. If we're looking here at our switch, if I open my switch, and I'm going to draw this just a little bit larger so y'all can see. We've got in, out. If I was to open my toggle switch, I lose my connection here. Doing pretty much exactly the same thing which we talked about with the fuse opening up. Your switch simply, or any control device, is simply going to connect and provide continuity for the circuit or disconnect. and not provide continuity for the circuit. So we would get voltage all the way up through here, but the voltage would not pass to here. And all the while we would have no current flow at all. So you don't always have to have current flow to have voltage. We can have pressure, but it's like an empty pressure, if that makes sense. So I can have voltage up to here, but no current flow. So just it's sort of a funky connection, but hopefully that makes sense. So our switch provides continuity or not provides continuity. And we can have a bunch of different types of switches. We can have one where it has multiple positions. So we've got a single pole, maybe double throw. Maybe if I want to connect my switch to something on this side or something on this side, we can have switches that are momentary contact, like your horn button. There's so many different types of switches. I won't get into it right now. I'll leave that again for an electrical class. There's a whole semester on this stuff. So all you need to know is that switches simply provide a connection for the circuit. Now, before we move from control devices, I think it's really important to talk about relays. So, without getting too crazy, I'll close my switch back up here so we have continuity in the circuit. But in some instances, besides a switch, another device that we can use to control a circuit is going to be what we call a relay. So, oh wow, let's try to put an A in there, relay. Relays look like this, and I'm just going to draw a simple, basic 4-pin relay. Again, not too crazy. What relays do is they allow a different kind of control in the circuit. Relays use a small amount of current to control a large amount of current. And so you don't always want to have a long circuit that is going to be really demanding, something like a starter circuit, have all this thick wire going to and from different parts of the vehicle. So what we'll do is to limit the amount of space that we're using that much current in, we'll use something like a relay. So just briefly, we have a coil side of the relay, and we have a switch side. We are going to use one side to control the other side. So if I put current through a coil of wire, I actually create a magnetism. And magnetism and electricity have a very special relationship because you can create one with the other and it goes both directions. If I have magnetism, I can create a current. If I have a current, I can create magnetism. Super fun. You'll learn more in an electrical class, so make sure you take that. So, if I run a current through this coil of wire, it will magnetize, pulling the switch down and making a connection on this side, providing continuity, almost as if you're flipping a switch yourself. So I have, rather than get into it in this video, because I don't want to make this video too long, I am going to put a relay video that I made previously. Hopefully it's a lot more detailed, so if you really want to know more about relays, you can watch this video. So I'll go ahead and attach that in Canvas. So I don't need to get into that now, but relays are a control device. That's what the symbol might look like as well. And that's as far as I'm going to go for control devices for the moment, because it's very easy to go down that rabbit hole. So moving along from control devices, we need to get into some of the fundamentals. We're going to start rolling into different types of more circuit related stuff, different types of voltages and things like that. And let's go back to our circuit here. It's really important to know where voltage should drop. I'm hoping by now I've led us up to the point to where we might start to have that idea, hopefully. So in my circuit, let's just say I've got I know it's 12.6 volts, I know, but just for the sake of easy math, we're going to talk about 12 volts batteries as just being just 12 volts for now. As this voltage passes through conductors or wires, these wires and all these connections to the fuse, out of the fuse, connects to the switch, all these connections and little bits of wire, they're not loads. They don't do anything. They don't produce light or heat or movement, and so they don't really use up voltage. Now, because of multiple connections, we do end up using a little bit of voltage. On the positive side of most circuits, it's usually about half a volt. On the negative side of circuits, it's usually about 0.2 volts max on either of how much voltage you're allowed to sort of use up in the circuit. This wire does nothing, so it should take up minimal voltage. As far as our basic circuits go, we're going to say it takes up 0. This is real life. It does normally take up a little bit of voltage, but those are your maxes. So we shouldn't take up any voltage in our wire here. Our fuse, again, is just simply circuit protection. It doesn't produce light. It doesn't produce heat. It doesn't produce movement. So we should have 12 volts coming out to the fuse, coming out of the fuse, and going into our switch. Does our switch do any work? Does it produce heat, light, or movement? No. So our switch, as long as it's making a connection, should transfer 12 volts from one side to the other side. Now take note, in order for voltage to get to the other side, the switch does have to be closed. It's almost like a moat gate, right? So it's got to be closed for anybody to pass through. If the moat gate is open, nobody passes. So if my switch is open, you will see a blockage. So 12 volts will come in and nothing will come out. So just keep that in mind. We'll play with that on the electro trainers in the next coming videos here. But when my switch is closed, the moat door is closed, it's not doing anything. It shouldn't be producing heat, light, or anything like that. So our switch shouldn't take up any voltage. All the way up to our load. Now in this circuit, we're using a light bulb. And that's essentially the electrical symbol, close enough for a light bulb in most wiring diagrams. But the load in the circuit, if you remember from our last video, we talked about what a circuit needs. The load in the circuit, or the circuit needs a load. It needs something to do. So what is a load? A load is going to produce movement, heat, or light. Or even magnetism, right? So I'm going to show you a couple common loads that you'll see. So right off the bat, there's your light bulb. Your light bulb will look like that. It produces light. It is a load. Now, there are different types of light bulbs. This is just going to be a filament style light bulb. There are LEDs and things like that. Many different symbols. We won't get into that in this class. Again, electrical or tune-up. We'll get into that stuff. So, besides a light bulb, I'll use a different color here. Besides a light bulb, we can use a resistor. That looks like a squiggly line. Resistors will actually produce a heat. So they use up voltage. Most of the time, resistors we use to maybe step down the voltage to purposefully use it up. And as a byproduct, they do heat up. But resistors use up voltage because they produce heat. There's a couple of other things as well. We can make this a variable resistor. Variable resistors, depending on if we turn it up or turn it down, you might have control over how much resistance that resistor has, and therefore maybe how much voltage it may take up. Another would be, let's say, a horn. Horns sort of look like this. They, depending on manufacturer, can be different. May have an H in there, and there will be connections in and out of a horn. Horns make sound. They produce an energy, so they take electrical energy and they turn it into sound. So they do take up voltage as well. What about any movements? So motors generally look like either just a circle or almost like a piece of candy, and it'll either say it'll usually have like an M or something in the middle there to let you know what it is. If it's a generator, then it may have a G. But movement of any sort, they generally tend to look like that. Now, I just talked about resistors, or I'm sorry, not resistors, relays a moment ago, and I said they have a coil of wire to create magnetism. Tends to look like this sort of squiggly line here, and what this symbol is it is either going to receive a current, or I'm sorry, a magnetism that is going to induce a current, or it is going to produce a current. That's its capability. It can go back and forth. But this coil of wire here, if I am creating it, like in a relay, if I am creating an electromagnet through a coil of wire, then it is going to use up voltage and count as a load in the circuit. So hopefully you take note of this. I know this is a lot to remember, but hopefully y'all are writing this stuff down because not everything is in the PowerPoint. So I don't like using PowerPoint for this particular section because I feel like there's a lot of dynamic things to talk about. There is one more I want to go and show you. It's not a load, but it can take up voltage depending on what direction electricity is going in. And that is a diode. So a diode will generally look like this. And that's the electrical symbol anyways. And it allows electricity in one direction, but not the other. It's very similar to, say, a check valve, right? So it'll allow in one direction, but not the other. They are used all over electronic circuits inside our vehicles. So in one direction, it will act simply as a wire, a regular conductor, and have no drop of voltage at all. But in the opposite direction, it will not allow current to pass, and so you will see a voltage drop. Again, more for an electrical class. Let's go back to where voltage should drop. So if I'm monitoring, let me use a good color that will stand out here. If I'm monitoring how much voltage is going to be here, how much voltage is going to be here, how much voltage is going to be here, and how much is going to be here. If we were to look at this, coming out of the battery, we've done no work yet. It's just a wire going into the fuse, so we should still have 12 volts. Coming out of my fuse, going into my switch, again, we haven't done any work yet. They're just making connections, so we should not have dropped any voltage or used any voltage. Now, in this case, if my switch is closed, we have continuity. Therefore, it's going to allow voltage to pass as well as current flow, Going into my light bulb, as long as everything's working properly, we should have 12 volts because throughout this whole part of the circuit, we haven't done anything. We haven't converted any energy yet. Now this light bulb, as it lights up, it's got continuity, it's got current flow. It's going to use up all that voltage, that pressure to do its job, which is to create light. And then by the time it's done, we should have 0 volts coming out of our light bulb. We should have used it all up. We're not allowed any voltage going back to the battery. If we do have voltage after the light bulb, either A, we have no continuity, or B, we have corrosion because I've got another load I need to get through. So if I don't have continuity, why would I have voltage afterward? Well, you may want to rewind or go back to the last video where I talked about continuity, because if you have no continuity, meaning no continuous path for current flow, it's blocked for some reason, then you cannot get any voltage drop. No work can be done. So what will happen is I have pressure coming up to the light bulb, but if I don't have, let's say, connection to chassis ground, I have no continuity. That pressure is an empty pressure, and I have no current flow behind that pressure or for that pressure to push. And so I can't really have real pressure, let's say in a water system, without the water, right? It would be an empty pressure. So it's important that we have continuity or a path for continuous flow. So that would be where voltage should drop and where it should not. If you see voltage drop in any one of these areas that it shouldn't, then you've got a problem, right? Maybe we've got corrosion, maybe we've got a bad connection. There's a number of things. In the last video in this series, I will talk about electrical faults, low resistance and high resistance faults, so you know what numbers you should be looking at. But that's essentially where voltage should drop and where it should not drop. Lastly, let's talk about AC and DC current, because we are going to run into that later when we talk about meters. I figured I'd squeeze it into this video here. So if we're talking AC and DC voltage or AC and DC current, this is what it's talking about. It's not talking about one of the best rock bands of all time. It's talking about current. AC is for alternating current. The symbol for AC is a squiggly line, generally on your meter, and a solid line of some sort. Sometimes it's dotted, but it's going to have a squiggly line. And what that means, if we're looking at if we're looking at, let's say, 0 volts, right? This is the line. We'll show kind of like a graph, right? For 0 volts. And up here I've got positive 1 volt, and down here I've got negative 1 volt. Alternating current means I am alternating, and let's take volt out of it, but just current itself, voltage, whatever you want to talk about. It is referring to going back and forth between positive and negative. Now, DC, on the other hand, is referring to direct current. And what that means is, first off, the symbol is a dotted line over a solid line. And what we're talking about here is, sorry, let me get rid of all this. Instead of alternating positive and negative, we are looking at a graph where my voltage is anywhere above 0. It does not alternate between positive and negative. That's what AC and DC are referring to. I won't necessarily get into signals because this is an Auto 50 class, but this is different than analog versus digital. Those are a different type of sine wave versus analog, or versus alternating current and direct current. So just wanted to throw that out there and thought that, you know, this would be a nice spot to put this. So the next video, we're going to go ahead and talk about the different types of circuits, and we're going to get straight into series circuits and characteristics and rules and all that fun stuff before we get into our parallel circuits. So this is a longer video. I apologize. I'm hoping my next video is not this long. I'm trying to get straight to the point. So if you have any questions at all, again, I remind you to make sure you post a comment or send me a message of some sort, and hopefully I can clarify. If you're on Canvas, then try to post it in the discussion boards on Canvas, because there might be plenty of other students who have the same exact question as you, and your question could really help them out. But I can't answer any questions you guys don't ask me, so make sure that you let me know if there's any confusion at all. See you in the next video.